people were not muted. Okay, we're ready to start. Welcome everybody to this year's Ithaca Fest 2023. We have switched the first two speakers, but don't worry that all three will speak. So our first speaker is Lavore, who's going to talk about evidential decision theory via partial Markov categories. Please, Elena, take it away.
Hello, everyone, and thank you for the invitation. Today, I'm going to talk about recent work with Maria Roman, and where we propose partial Markov categories and discrete partial Markov categories to model evidential decision theory. So I will start with some motivation and by describing a decision problem and how to solve it with evidential decision theory. And then I will define partial Markov categories and discrete partial Markov categories. And finally, I will show how we can use this formalism to state and prove bias theorem and to talk about observations and updates. Okay, so the decision problem that I would like to talk about is known as Newcomb's problem. Can you see the titles? Because they're covered for me, but maybe you see them. Okay. Oh, whoops. Okay. And why is this problem famous? Because depending on which decision theory you choose, then the solution is different. But let's see what this problem is about. So there is one agent, which is in front of two boxes. The first box is transparent and contains €1. And the second box is opaque, and it's filled with either 10,000 euros or it's empty. Then the agent can choose to either one box, which means just taking the opaque box, or two box, which means taking both boxes. But we know something more about this opaque box, and this is a bit confusing sometimes, but we know that this box was filled by a predictor. This predictor predicts the action of the agent, and if it thinks that the agent will one box, then it fills it with 10,000 euros. If the predictor thinks that the agent will two box, then it leaves the box empty. Now, we also know that this predictor is very accurate. Let's say that it's right 90% of the times. If you're the agent, what should you do? There are various ways in which you can reason, and two of the most famous ones are causal decision theory and evidential decision theory. Let's see, if you decide to reason with causal decision theory, the thing you ask yourself is, which action would cause the best scenario? So you go to your utility table and you say, well, whatever the predictor did, I get €1 more if I take both boxes. So I will two box. On the other hand, if you decide to follow evidential decision theory, then you ask yourself, which action would be evidence for the best case scenario? So you go to your utility table and you reason like this. So if I one box, then this is evidence for the prediction being one boxing. So if I one box, I expect the predictor to have predicted it. So I expect the box to be full. On the other hand, if I two box, I also expect that the predictor predicted it. So I expect the opaque box to be empty, so I get just €1. So with this reasoning, the thing that I should do is one box, because what the two scenarios between which I'm really choosing are these two. So it's better to one box. if we compare the two decision theories, we see that the causal decision theorist, on average, would get 1,001 euros, while the evidential decision theorist will get 9,000 euros on average. So in this case, evidential decision theory is better. So why did I take this example? My point was not to convince you that evidential decision theory is better than the other one, but just to show that it's not easy to reason with decision problems, and it's not completely obvious how to formalize the statement of the problems and how to reason about them. So maybe we would like to draw a diagram like this one for our Newcomb problem, because we have a predictor, it makes a prediction, and this prediction influences the outcome, the utility, but also it needs to be compared with the action of the agent, because we know that it will be most of the times the same thing as the action of the agent. So if we want to give a semantics to this diagram, we want a semantic universe that is able to express probabilities, but also constraints. What's a simple example? Well, subdistributions. What's a subdistribution? A subdistribution on A is just a distribution on A plus 1. So the things that can happen are the things in A or failure, this plus 1. So we can encode subdistributions as functions from A to the interval 0, 1, such that the support is finite, but more importantly, the total probability mass is at most 1. So it's not exactly 1 because we allow some probability of failure. Subdistributions give a monad on set because there is a distributive law between the finitary distribution monad and the maybe monad. So we can consider its Kleisli category. A morphism in this Kleisli category can be thought of as a stochastic channel or a stochastic computation that can also fail. So if we evaluate our channel on A given X, we think of it as the probability of the output being A, given then the input was X. And similarly with the probability of failure, we have a probability of failure for every input. Composition is similar to composition in Kleisli of the distribution monad. So we just multiply the probabilities of F and G and we sum over the internal wire. And for the probability of failure, the composition can fail either when F fails or when F succeeds and then G fails. This Kleisli category also has equality checks that are lifted from partial functions. So we have a morphism of this type that when the two inputs are the same, it just returns that input. When they're different, it fails. Okay, so if we want to read Newcomb's diagram in subdistributions, we can compute the probability of getting a utility and a given action. We just multiply all the probabilities that we get from the diagram, and we sum over the internal wire, which is just this one. And we moreover have this constraint that the output of N is the same as the action of the agent. And then the probability of failure, if we assume that all the blocks are total. It's just the probability that the output of n is different from the action of the agent. So we discard or we throw away all the scenarios in which these two are different. Okay, so if we want a calculus to reason with diagrams of this kind, we want this calculus to be able to express stochastic processes and partiality and constraints. And what we propose is discrete partial microcategories. So are there any questions so far? Anyway, feel free to interrupt me if you have any questions at any point. Okay, so what's the idea behind partial Markov categories and discrete partial Markov categories? But we take Markov categories with conditionals and we add partiality to it, or we take discrete Cartesian restriction categories and we add probability to them. Or better, we drop the totality axiom from Markov categories with conditionals, or we drop the determinism axiom from the discrete Cartesian restriction categories. So let's slowly build up to them, to the definition, starting from copy discard categories, which are also known as GS monoidal categories. What are they? So they're symmetric monoidal categories where every object has a co-commutative comonoid structure that satisfies this axiom here. And that is also uniform, which means that it respects the monoidal structure of the category. And importantly, we don't require naturality of either the copy or the discard. So morphisms can be non-deterministic and non-total. Then, if we want to talk about probabilities, we may want to consider Markov categories with conditionals. And what are they? So there are copy discard categories where morphisms have conditionals. So if I have a process with two outputs, I can write it in such a way that one of the two outputs is produced first, and then it is used to produce the second output. And for Markov categories, we also ask that all morphisms are total, which is the axiom that we're going to drop. But before dropping it, we want to understand what's the role of it in Markov categories. And one thing that it does for us is that it gives nice marginals. So marginals in a Markov category with conditionals they are as expected, meaning that the marginal of F on A is obtained by discarding the B output. And the proof is very simple. It relies on, of course, conditionals, but also totality. So the conditional needs to be total, like every morphism in a Markov category, but in particular, this one. So if we want to keep this property for partial Markov categories, what should we ask? Should we ask all conditionals to be total? No, because that's too strong. They don't exist even in a Kleisli of subdistributions. But then if we don't impose any condition on conditionals, they're a bit too wild. So we found a sweet spot in the middle, which is asking them to be quasi-total. And this allows us to prove also that they give nice marginals, so we're happy. And what does it mean to be quasi-total? So a morphism is quasi-total if its probability of failure is deterministic. So for every input, the morphism F either certainly fails or it's a total distribution. This means that we can talk about the domain of definition of F, which is where the set of inputs in which F is total. And we call it like that because in restriction categories, it's also called the domain of definition. Okay, so what's a partial Markov category? It's a copy discard category with quasi-total conditionals. So we have the same condition, the conditionals with the same definition as in Markov categories, but we ask that the conditionals have a domain of definition. Okay, now we want to add constraints. And we're going to take inspiration from discrete Cartesian restriction categories, where, and what are they? They are copy discard categories with an additional piece of structure, which is the comparator. And we ask two equations that say that it behaves like an equality check. So copying and then checking that they're equal is the same as doing identity, and checking that the two inputs are equal and then copying them is the same as the other way around. In restriction categories, usually they talk about deterministic morphisms. So the copy is asked to be natural, but we're not going to impose that because we want to talk about probability. So we define discrete partial Markov categories, which are partial Markov categories. So we have our copy discard structure, we have conditionals, and they're quasi-total. Plus, we ask this additional piece of structure that is the comparator, and we ask that it behaves like an equality check. Okay, so what are examples? Well, the Kleisli category, the subdistribution monad, is a discrete Cartesian, it's a discrete partial Markov category. But for every Markov category that has conditionals already and has coproducts, we can consider the Kleisli category of the maybe monad on it. And if this maybe monad satisfies some ugly technical conditions, then the Kleisli category is a partial Markov category. And that happens for the Giri monad on standard variable spaces as well. Okay. Are there any questions so far? So I think if you want to remember one thing, just one thing from this talk, this is a good slide to remember. But if there are no questions, I guess I can move on. I can move on to observations, updates, and bias. Okay, so we can define bias inversions in the same way they're defined in Markov categories with conditionals. So if we have a prior and a channel G, I can take the bias inversion of the channel with respect to that prior by just conditioning on A. So this was done in Markov categories as well. But one thing that, of course, was not possible in Markov categories was normalization, because in Markov categories, every morphism is total, so you don't need normalizations. But in this case, morphisms can be partial, so you may want to consider their normalization, so their total counterpart. And you can also define normalizations via conditionals by conditioning F on the monoidal unit. So what you get is a marginal, and the conditional is the normalization of F. Okay. Then we can state bias theorem in any discrete partial Markov category, which I find cute. So, okay, what's the statement? If we have a deterministic observation, A, and a prior, sigma, and we observe it through a channel C. Then we can update our prior sigma, and we obtain a posterior that is proportional to the bias inversion C dagger sigma evaluated on A. This is the diagram corresponding to this statement. And why is this bias theorem? So this formula is what is usually called bias theorem. And we see, let's see, where are all these pieces? So the probability of X given the observation small a is given by this component, while this component here is the probability of a, small a, given X times the probability of X given by sigma. And then there's this normalization factor, which is the denominator. So I have, again, the probability of small a given X, given, well, Y, times the probability of X equals Y. And then I sum over the internal wire. Now with string diagrams, it's super nice to prove this. So we take the right-hand side, we start from it, and we condition. So we invert the channel. Then we use the Frobenius axioms to rewrite this diagram into this diagram. And we use determinism of our observation to copy it. Since it's deterministic, we can copy it, and we obtain the left-hand side. Okay. We can also express Peirce and Jeffreys updates. There are two ways of updating on evidence, which depend on what type of evidence one has. So I have a prior sigma, I have a channel C, and I observe either a co-state, so a Q, or I can observe a state, so tau. And then I can update on these two kinds of evidence by taking bias inversions, and I obtain my posteriors like this. And we can show that whenever your observation is deterministic, Peirce update on the co-state corresponding to A coincides with Jeffreys' update on the state A. This was already proven by Jacobs in the particular case of subdistributions, but this holds in any discrete partial Markov category. Okay. Now at this point you may wonder, okay, but what if I have a partial Markov category that doesn't have comparators? How do I do observations? So one nice thing you can do is to freely add deterministic observations to your Markov category with conditionals. So I give you a Markov category C that has conditionals, and then I freely add a co-state A opposite for every deterministic state in C, and then I quotient by this axiom, which what is imposing really, if we think of our co-state as observing A, this equation is applying the Frobenius axioms and the fact that A is deterministic. Okay, so this construction gives a partial Markov category that has deterministic observations. And we can compute normalizations and conditionals inside this category by only taking conditionals in the old Markov category C. Okay, and I think that's all for me. So summary, we define discrete partial Markov categories and partial Markov categories. And I think the thing I want you to remember is the definition, this one. So we have a Covey-Descartes structure, we have conditionals, and they are quasi-total. And if you want the discrete structure as well, you want to ask for comparators that behave like equality checks. So thank you for listening, and I'm happy to take any questions.
Very good. Thank you for the speakers. Several words of round of applause. And all right, are there any questions? Feel free to unmute yourself. We have quite a bit of time for questions. So maybe in the meantime, to break the ice, I have a couple of questions. One is I might have missed. So this was motivated by, well, evidential decision theory, right?
Mm-hmm.
So can you clarify a little bit the link, or maybe repeat the link?
The link, yeah, right. So let's go back to. Okay, yeah, I think the nicest thing is that you can read diagrams like this, and if you go at other, if you look at other decision problems, you can always express them as a diagram that has a state that tells you how, let's say, the world behaves, and then this state is a bipartite state, and one part goes to, let's say, the utility function, or a part on the right, and the other output, I should have drawn the diagram, but I thought I didn't have time to talk about it, so I didn't. But so the other output is what the agent can observe of the world. In this case, there's no observation, but you could imagine that there is an observation here. And then there is the last part of the diagram that computes the utility and imposes some conditions on, like some compatibility conditions between the agent and the world, the environment. And when you want to solve a problem with evidential decision theory, what you do is you plug here into the A output an observation, a deterministic observation of your action A. And then you can reduce the diagram using the Frobenius axioms to something smaller. And then you compute that for every possible action A. And you get for every A, you get a distribution on the utilities. And that's what you want to maximize, like the average of your utility. So that's explained a bit better in the paper.
Thank you. Just to clarify, where do we see the averaging part in the string diagrams?
There's no averaging here.
Ah, okay. So that's like on top at the end sometimes.
Yeah.
I see. Okay, could that be codified by using like the algebras of the monad?
Maybe. I haven't thought of that actually, but maybe.
Okay, I don't know.
But
Okay, thank you for answering, by the way. That helps a lot. Are there other questions? Doesn't seem so. Okay, I have another question. So you call this structure that allows for comparison a discrete partial Markov category.
Mm-hmm.
I suppose that there should be, I guess this is something like for general measurable spaces, or like standard Borel, something with continuous fails. Is this the idea? Or if not, what motivates the name?
Mm-hmm. So for restriction categories, Cartesian restriction categories, the ones that have this comparator structure are called discrete. So that's where the name comes from. And But standard Borel spaces, or the Kleisli category of the Geary monad on of the sub-Geary monad on standard Borel spaces, it does have comparators, but they behave not very nicely, because if you compare with a deterministic observation, then everything goes to 0, because the probability that you observe a specific point is 0. So that's not nice. But let's say that that's a reason to consider, instead of the comparator structure that you have, the one that you can add freely. So you can still do deterministic observations, like exact observations, by just adding them freely. And then you can compute in your original Markov category because of these results.
I see. Very nice. Very nice. Thank you.
Yeah, thank you.
Are there more questions? We still have about 10 minutes before the next talk. Tobias, you have a question?
Yeah, yes, just briefly. So very nice.
Thank you.
Just to make sure I understood correctly, can you go back to the slide of the synthetic Bayes theorem?
Yes. Or maybe this one.
Yep, I think there on the right-hand side in the string diagram, you have kind of an implicit normalization, right? That's where the denominator comes from, in the sense of the previous slide, net normalization.
So the normalization would be to divide this one.
Oh, that's part
by
of the
this
equation.
scalar.
Sorry. Okay. Yes, I get it. Okay. Yeah. Sorry, I hadn't realized this was part of.
Yeah. Thank you. Thank you for the question.
Great. Are there any more questions?
Oh, but yeah, I think you could also use the normalization notion of normalization from the previous slide, could you?
Yes, you could.
Okay, yeah.
Yeah, in fact, I mean, that's sort of what you do, because normalizing is just taking conditionals. And here, this is in the end a conditional.
Yep. Okay, thanks.
Thank you.
All right. Any additional question or comment?
I have a question. You mentioned that
Please.
when you have deterministic observations, that then the system collapses, because then the probability of observing another point is 0. Now, my question is, can you define deterministic observation as with a limiting process? Like make them, and how would that change the formalism? So make them probabilistic, but with a limit operation. Could you integrate them in such a way in the formalism?
Maybe. So we haven't thought of that specifically, mainly because this, let's say that this thing happens only in some examples. It's not like a syntactic thing, but it would be interesting to just remove deterministic observations, and the only observations that you can do are probabilistic, but then you can take the limit. Yeah, it would be very interesting to consider. Thank you for the question. But yeah, we haven't thought of it.
Thank you.
If I may add to that, one of the problems that arises when doing things like that is the so-called Borel's paradox, that if one tries to form conditionals by limiting over like a small non-zero measure set that tends to a point, the shape of the limit, as in how you actually tend to the point, depending on which space we are, from a square, rectangle, or circle, might actually change the limit, which means that if one takes all the possible paths, then the limit in the topological sense doesn't exist. So there are situations where this works, of course, but in general, it's problematic. So one needs a lot of care for these things. But of course, this is assuming we're doing something in measurable sets. And as you said, Like it's not a syntactic construction.
Yeah.
Okay, thank you for the question, by the way. Anybody else? Okay, doesn't seem for now, so let's thank the speaker again.
Thank you.